Lewis dot structures is where we first learn to start visualizing more complicated molecules. And we need to visualize more complicated molecules so we can tell if they're polar or nonpolar. Because if they're polar or nonpolar, that's going to help us determine some of their physical properties. When we visualize chemical structures, first you need to remember that chemical bonding is only with the valence electrons. These are the only guys that play chemistry games. And that's what we're going to use for the Lewis dot structures, developed by a guy whose last name really was Lewis, Gilbert Lewis, as a matter of fact. There's only a couple of hard, fast rules for valence dot structures. And notice this is a little bit different than Lewis dot structures just because this helps us visualize the valence electrons. Hydrogen has one valence electron, so we usually write it like that. Truthfully, though, it doesn't matter if you write that single dot. This single dot is the electron, by the way. It doesn't matter if you wrote it on top or on the side or on the bottom. That doesn't matter. You just need to be able to show that hydrogen has one valence electron, and we show it with a single dot. Helium, then, has how many valence electrons? Well, although it is in column 18, it does have two valence electrons. If you recall, for the 1s orbital, which both of them are in, is in that first energy level, the 1s orbital can only hold two electrons. So when hydrogen looks like this, it feels like that. This is called the duet rule, and hydrogen is the only atom that is happy with the duet rule. Duet, of course, means two. So if we were to take a look at the Lewis dot structure for hydrogen, hydrogen by itself has one valence electron, and I add to it another hydrogen with one valence electron, and I make the hydrogen molecule. Each of these single atoms thinks it has two electrons in the outer shell. So each one of these is happy. They both end up feeling like helium because they share these two valence electrons. Two electrons for every single bond. Every bond only has two electrons. To look at the valence electrons for lithium, well, lithium is in which column? Yep, it's in column 1. So lithium has one valence electron. And again, I don't care which side you draw this on. Beryllium, well, that one has two valence electrons, and we draw them on opposite sides. Those electrons want to be as far apart as possible. Boron, well, I draw it like this, because boron has three valence electrons. Carbon, we draw it like this, because it has four. Nitrogen has 5 valence electrons. I bet you can guess how many oxygen has. You said 6, you're right. And fluorine, how many does fluorine have? Well, if you said 8, you're wrong. It's not 8. How many? 7 is correct. And then finally we get to neon, and neon has 8 valence electrons. And that same trend continues all the way down. That's why they're organized in the families that they're organized in, because these guys want those same number of valence electrons. Just look at the electron configuration, to be truthful. Anyway, this is called the octet rule. And all of these atoms, well, not beryllium, we'll ignore beryllium for a while, but all of these atoms, oh, we better ignore boron. Yeah, we're going to ignore boron for a while. But all the rest of these, it's the octet rule. These guys all want 8 electrons. That's their goal. And that's called the octet rule. So we only have 2 rules we're going to deal with right now. And that's the duet rule, and that's only for hydrogen, and then the octet rule for everybody else. So here's the steps for drawing Lewis dot structures. The first thing you need to do is write the formula. Well, this in black, and I know it's kind of hard to see, but in black what we're trying to do is we're trying to find the Lewis dot structure for water. So I think you can write the chemical formula for water without any problems. Oh, look, and I even put it there for you. Then we need to count the total number of valence electrons. To do that, to count the total number of valence electrons, let's first look at how many valence electrons does hydrogen have. Hydrogen has 1. This hydrogen, because remember we're dealing with H2O, and this hydrogen has 1 valence electron. Oxygen has 6 valence electrons. So the total number of valence electrons that that water has is 8. That's just the second step. The third step is to count the number of electrons it wishes it had. Hydrogen wishes it looked just like helium, so it has a wish for 2 electrons. And this one also. And oxygen wished it looked just like neon, so it wishes it had 8. So the total number of electrons that water wishes it had is 12 electrons. The fourth step is we need to subtract what water wishes it had from what it actually has. And that gives us 4. These are the number of bonding electrons water has. Now, if you recall, every bond has 2 electrons. If you don't have 2 electrons, you don't have a bond. So I took this number that I subtracted from step 4, divided it by 2, so now I know water is going to have 2 bonds. This last step is probably the most difficult step in drawing Lewis structures, and sometimes it's just trial and error. I can give you a couple of tips. Tip number 1, is that how I want to say it? No. Most of the time, I can do it that way. Most of the time, well, or even pretty much all of the time, we'll even change that to all of the time, hydrogen is on the outside of the molecule. Because hydrogen only wants 2 electrons, so hydrogen's only going to have 1 bond. That's why it's on the outside of the molecule. The second general guideline is that the least electronegative atom is usually in the center. Usually. And then we'll take a look at bonding versus lone pairs. So let's first draw the molecule and ignore that for a second. Well, let's start with oxygen, because this is H2O. And while the least electronegative is usually in the center, hydrogen has to be on the outside. So I'm going to draw it like this. The reason that I could not have drawn it like this is this makes the middle hydrogen have 2 bonds for a total of 4 electrons. And hydrogen does not want 4 electrons. Nope. Hydrogen is perfectly happy with 2. And that's why I said hydrogen needs to go on the outside like I did in the first molecule. So I'm going to go ahead and erase all this. All right. Now, then we need to take a look at whether or not each one of these guys are happy. Did you place all of the electrons? Well, if you recall, water has 8 electrons, and the molecule has to have these 8 electrons. And right now, I put 2 electrons there and 2 there. So I have only placed 4 electrons. I have 4 electrons left. So somewhere on this molecule, I need to put 2 more pairs. Is this hydrogen happy? Yes. Is hydrogen's happy when it only has 2 and it feels like 2 with that bond? And this hydrogen's happy, but oxygen's not. Oxygen only feels like it has 4 electrons around it. But if I put these electrons like this, these are these 4 electrons, 2 on the top, 2 on the bottom, oxygen now feels like it has 8 electrons around it. There's 2 electrons there, 2 there, 3, there's 2 more, and 2 more. So now oxygen feels like it has 8 electrons. The electrons that are in the bonds, we call these bonding pairs. These electrons I draw like this as dots. These are called lone pairs. And as long as oxygen has 8 total electrons around it, it could care less if they're bonding or lone. And hydrogen, as long as it's bonding or lone pairs, well, hydrogen I don't think will ever have lone pairs on it, but it's happy with 2. That's pretty much all there is to it. All right, let's do some more practice with this. We're going to assume that hydrochloric acid is covalent. There's some argument about whether or not it's actually covalent or ionic, and it kind of lies somewhere in that spectrum, but you can draw it either way in all honesty. Okay, hydrochloric acid has the formula of HCl. So what's the first thing we need to do? Well, we have to count how many electrons this thing has. Hydrogen has 1 electron. Chlorine has 7 electrons. So this molecule has 8. Now we have to figure out how many this guy wants. Hydrogen wants 2. Chlorine wants 8. And that's a total of 10 electrons. Now, the next step says you need to subtract these 2 numbers. So that gives us 2 electrons. Now I have to find out how many bonds there are. And because there's 2 electrons in every bond, I'm going to take the number of electrons left over and divide that by 2. So that's going to equal 1 bond. So now I know hydrochloric acid has 1 bond. I can go ahead and draw this molecule with 1 bond. 1 bond. Now this guy had 8 electrons. How many did I just put on there? That's correct. I put 2 on there, so I have 6 electrons left to put on the molecule. Is hydrogen happy? Yep, it's got 2 on it, so it's good, but chlorine's not very happy. It really wants 8. It only feels like it has 2. So if I take those 6 electrons, put it around chlorine like this, now chlorine's happy. It now feels happy with 8 electrons around it, and hydrogen's happy. Yeah, they do get more complicated than this, I promise. All right, so the Lewis structure for carbon tetrachloride. Well, first we got to have the formula, so CCl4. We have to figure out how many electrons, valence electrons, this guy has. Well, carbon has 4 valence electrons, and chlorine, well, there's 4 chlorines, and each one of these guys has 7, so that's 28. So this molecule has 32 electrons. Go ahead and pause the video and see if you can figure out how many this guy wants. Well, carbon wants 8, and chlorine, there's 4 of them, and each of those guys want 8. So this guy has a total of wanting 40 electrons. Now what do we do? That's right, we subtract these 2 numbers. So when I do that, I end up with 8 bonding electrons. If these are the number of bonding electrons, how many bonds do we have? Well, we got to divide that by 2, so now we know we have 4 bonds. The least electronegative atom goes in the middle, and carbon. Carbon is a big-time middle guy, so he's going to go in the center anyway. And there's 4 chlorines that are going to come off of it. Oh wow, look at that. That just gave us our 4 bonds that we were supposed to have. Are we done? No. Even though carbon's happy, chlorine's certainly not. Carbon, each of these chlorines thinks it only has 2 electrons. That's not going to do it. We had 32 electrons to put on this molecule, and I've only put on 2, 4, 6, 8 of them. So now that I have 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, and 32. Yeah, that's pretty good. Let me show you some of the pictures I've often gotten for this, which are incorrect. And let's look at why they might not be correct. One carbon tetrachloride molecule I've seen come in before is this one. Yeah, that kind of violates the rule of putting the least electronegative in the center. And when you put things in a big old line like this, the electrons just are not as far away apart as they possibly can get. And that's one of your goals, is to get them as far apart. Now let's see if on this straight lined one I can still fit 32 electrons. 2, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Well, that's not going to work because I could not get all of the electrons on this molecule, so that one does not work. If you can't arrange them in a way that gets all of the electrons around it, you'll need to try again. Most of the time you're going to have a central atom like I have here with all of the other ones coming off of it. It's very rare to have something that like the one in the green. Okay, let's try phosphorus trihydride. Okay, well, here's the formula for phosphorus trihydride. Oops, that's not it. I drew phosphorus iodide. Okay, phosphorus trihydride. Okay, the first thing you need to do is figure out how many electrons this guy has. Well, phosphorus has 5 electrons, and hydrogen, well, there's 3 of them, and each one of those has 1. So this guy has 8 electrons. Now we have to figure out how many it wants. Phosphorus wants 8. Hydrogen has 3 atoms, and each one of these atoms wants 2 electrons. So we end up with 14 electrons. What's your next step? Well, you do need to subtract these. So when I do that, I end up with 6 bonding electrons. These are the ones involved in bonds. To divide by 2 so I can get the number of bonds gives us 3 bonds. Phosphorus and hydrogen are equal when it comes to electronegativity, but I'm going to go with phosphorus as the one in the center because hydrogen needs to be on the outside. So phosphorus with 3 hydrogens coming off of it. Well, that makes all the hydrogens happy, but phosphorus 246 is not happy. Phosphorus wants 8. I had 8 electrons to place. I've only placed 6, 2, 4, 6, 7, 8. Phosphorus has a lone pair and 3 bonding pairs, and now phosphorus is quite content. I know this is not on your packet, but you need to do it anyway, because you definitely need more practice. So ammonia, well, that's NH3. Now pause the video, see if you can get all the way through drawing the Lewis structure without my help. And if you can't, that's okay, I have more practice. Well, first we have to figure out how many it has. Nitrogen has 5 electrons. Hydrogen, well, there's 3 of them and each has 1. So that's a total of 8 electrons. Now, how many does this guy want? Nitrogen, oh, so wishes it had 8. And hydrogen, there's 3 of them and each wished they had 2. So that's 14 electrons. Subtracting these 2, we end up with 6 bonding electrons. And since there's 2 electrons in every bond, we find out there's 3 bonds. Even though hydrogen is less electronegative than nitrogen, since hydrogen has to be on the outside, that means nitrogen has to be the center one. I'll draw the hydrogens coming off of that. Am I done? Well, the hydrogens are certainly happy. Each one of those has 2, but nitrogen's not very happy, and plus I had 8 electrons to put on it. So I'm going to put 2 more here. So with the lone pair and 3 bonding pairs, nitrogen now feels like it has 8, and life is good. Try this one for methane. Okay, so what? Did I hear you say you need the formula for methane? Oh, fine. There you go. Pause the video, see how far you can get. Let's see, this guy has, so carbon has 4 electrons. Hydrogen, there's 4 of them, each has 1, so that's 8 electrons. And in terms of wants, carbon wants 8, hydrogen, there's 4 of them, each want 2, so that's 16 electrons. When I subtract these two, I end up with 8 bonding electrons. This is how many electrons are going to be in the bonds. Each bond contains 2 electrons, so we have 4 bonds. Hydrogen's got to be on the outside, and carbon's a big center guy. So we'll draw a carbon with the 4 hydrogens coming off of it. And are we done? Yeah, because look, carbon has 4 bonds, 8 electrons around it. Hydrogen is all happy with 2, and we only had 8 to place. These do get harder, by the way, just to let you know. Oh, look, one that's a little harder. Well, let's try ethane. Well, go ahead and see what you can do with it. No, really, pause it, see what you can do. Oh, all right, fine. Well, first we have to figure out what this guy has. So each carbon, there's 2 of them, has 4 valence electrons. Hydrogen, there's 6 of them, and each one of them has 1 valence electron. So 2 times 4 is 8, plus 6, this has 14 electrons. Now, how many does ethane want? Carbon really wants 8, and there's 2 of them. And hydrogen, all 6 of them really want 2. Well, 2 times 8, that's 16, and 2 times 6, that's 12. So this guy wants 28 electrons. Yeah, that's not going to happen. We only have 14. Well, let's figure out how many electrons there are in the bonds. So I need to subtract 28 from 14. Well, I said that wrong. 14 from 28. So we have 14 electrons that are bonded. This is 14 bonding electrons. So I need to divide by 2, and I find out I have 7 bonds. Now you have to figure out how you're going to draw this thing. You know for a fact hydrogens have to be on the outside because they can't have more than 1 bond. And I have these 2 carbons in the center. I'm going to draw them like that. Now let's see what we can do with these 6 hydrogens. I've done 1 bond, so I need 6 bonds more. 1 bond, 2 bonds, 3 bonds, 4 bonds, 5 bonds, 6 bonds. Well, that satisfied my 7 bonds. Did I place all the electrons? 2, 4, 6, 8, 10, 12, 14. Oh, that wasn't that hard, was it? Let's try another one.
No.
Now don't get all excited with the 3, 2, 1s and think I'm all done lecturing. This is the end. This is not the end. This is just more practice. So it's an opportunity for you to practice a few of these all on your own. We are going to need the chemical formula for carbon monoxide. Okay, so carbon monoxide. And just like before, we're going to count how many this guy has and how many it wants and how many bonds. All right, so first off, how many does this have? Well, carbon has 4 valence electrons. Oxygen has 6 for a total of 10 valence electrons. And in terms of what it wants, well, carbon wishes it had 8 valence electrons, and so does oxygen. And that's 16 valence electrons. When I subtract these, I end up with 6 bonding electrons divided by 2 gives me 3 bonds. How on earth am I going to get 3 bonds between 2 atoms? Yeah, multiple bonds. How many bonds? 3. 1, 2, 3 bonds. Am I done? No, neither carbon or oxygen is very happy right now because look at this. 2, 4, 6. They think they only have 6 electrons around them, and I had 10 to place anyway. So how am I going to place the leftover 4 electrons?
Magic.
Magic won't do it, so I'm going to have a set here and a set here. Now notice this pair plus these 3 makes 8, and this pair plus these 3 makes 8. Now they're both happy, and it wasn't magic. Carbon dioxide. Pause the video, see if you can do this one on your own. Oh, you want the formula for carbon dioxide? Okay, fine. Now pause it. All right, has. Carbon has 4. Oxygen, well, there's 2 of them. Each have 6. So that's 16 electrons. And it wants, well, carbon wants 8. Oxygen, there's 2 of them. And that one wants 8. So that's 24 electrons. And when I subtract those, see 24 minus 16, that's 8 electrons. 8 bonding electrons, divided by 2 for 2 per bond, and I end up with 4 bonds. Okay, well, if you got that far, that's great. What did you end up drawing? Well, if you put carbon in the center, that's a good move for 2 reasons. One, he's a big center guy. See, C for center, right. And oxygen's more electronegative, so they're definitely going to go on the outside. There's a couple of ways you could have drawn this. Only one of them was correct. The correct way, let's see, we put an oxygen on each side of it, but that's only 2 bonds. We need 4. So we put an additional bond there. We now have 4 bonds, and carbon's quite happy. But we're not done. Because 2, 4, 6, 8, I've only put 8 electrons on here, and I had 16, so where are you going to put the other 8? Well, in order for this oxygen to be happy, it needs 8 electrons. 2, 4, 5, 6, 7, 8. And this one, 1, 2, 3, 4, 5, 6, 7, 8. Now they're happy. What if you had drawn the molecule like this? Would that have worked? You could have gotten the 16 electrons around that. That is true. However, carbon is not in the center, which is a problem, because these are much more electronegative than carbon. And carbon needs to go in the center, and the most electronegative should try to be on the outside. So that one's not going to work. Sulfur trioxide. Try this one all on your own. Oh, you want the formula? Okay, there's the formula. Let's calculate the has. Sulfur has 6 valence electrons. Oxygen, there's 3 of them. They all have 6 valence electrons. So that's 24 electrons. Now for the once. Sulfur wishes it had 8. And every single one of these oxygens wishes it had 8. So that's 32 electrons. So when I subtract these two, I end up with 8 bonding electrons. Because there's 2 electrons in every bond, you end up with 4 bonds. Sulfur is less electronegative, and often the first one's going to be your central atom. And these almost always end up looking like some sort of flower doohickey thing. There we go. Is everybody happy? Oh, I only put 3 bonds on here, and I have 4 bonds. It does not matter where you put the double bond. It's this thing called resonance, and this double bond actually flips between them, but that's more information than you wanted. The point is, you don't care. It doesn't matter. You can put it on any one of those. Well, look at this. Sulfur now feels like it has 8 electrons. 1, 2, 3, and 4. 4 bonds times 2, 8 electrons. It's pretty happy. Have I put all 24 electrons on this molecule? 2, 4, 6, 8. No, I have not. Well, 8 9, 10, 11, 12. Well, that oxygen's happy now. 13, 14, 15, 16, 17, 18. Now that one's happy. 19, 20, 21, 22, 23, and 24. Now we're done. Don't get so excited and think this is the end of the video because I have an extra practice problem here. It's not the end. Sorry. I know I've got a few more things to talk about, or maybe just one more thing, but try this problem on your own. Let me see how you do. And try this one on your own and bring it in and let me see how you did. Now we're going to do Lewis dot structures of ions. Don't roll your eyes. Okay, so we need the Lewis structure for the nitrite ion. Oh, goody, polyatomics. Nitrite. Nitrite is NO2 with a -1 charge. Just like before, we need to figure out how many valence electrons this guy has. Nitrogen has 5 valence electrons. Oxygen, there's 2 of them, and each has 6. And you see this negative right there? That negative means we have 1 more valence electron. Now we can add them all up. 12, 13, and 18 electrons. Now for the ones. Nitrogen wants 8. Oxygen, we have 2 of them. That also wants 8. And we don't count the lone, that charge on here, because the charge doesn't want anything. It just is part of what it has. So we have 16 and 8, that's 24 electrons. Subtracting these two, we end up with 6 bonding electrons. Divide by 2 gives us 3 bonds. Nitrogen is the first one. It is less electronegative than oxygen, so that works out well. And we need 3 bonds, so I'm going to put oxygens on either side. That takes care of 2. Where do you want to put the 3rd bond? Well, truthfully, it doesn't matter. You can put it on either side. We have 18 electrons to place. We've only put on 6. 2, 4, 6. Now what? Well, let's try. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. One more thing to do for an ion. Ions have a special notation. Yay, aren't you excited? Yeah, we have to put brackets around it and show the charge up there. Now you are done with an ion. You try carbonate on your own. See how you do when you hit place. That means you have to pause it. First, I'll give you the carbonate ion. And just like before, we need to figure out how many valence electrons this has. Well, carbon, there's 1 of them, and it has 4 valence electrons. That really is a 4. And oxygen, there are 3 of these guys, and they each have 6. And this -2 means that this molecule is gained, or rather this ion has gained 2 electrons. So we have to include those 2 here. So we end up with 24 valence electrons. How many does it want? Carbon wants 8. Oxygen, there's 3 of them, and they all want 8. And that's it. This guy, these extra electrons, they don't want anything. They're just there. That ends up with 32 electrons. 8 bonding electrons divided by 2 means we have 4 bonds. Who's going to go in the center for this molecule? That's right, carbon's the center guy. And he's the least electronegative one. So let's put the 3 oxygens around it. Yet I have 1 more bond to place. Where do you want to put it? It doesn't matter. Just pick one. Remember resonance structures? I mentioned it briefly and said you don't really need to know, but the point is that flips, so it doesn't much matter. Now we have to make sure all 24 electrons are on this molecule. We've done 2, 4, 6, and 8. 9, 10, 11, 12. That puts 8 around this oxygen. 13, 14, 15, 16, 17, 18. That puts 8 around this oxygen. 19, 20, 21, 22, 23, 24. Are we done? No, we're not. Remember, there's that funny notation we have to use for ions. You need to put the ion in brackets and put the charge on it. Now you're done with carbonate. Again, try phosphate on your own before you hit play and see how you do. Right, phosphate is PO4, 3 negative. So this has phosphorus has 5 valence electrons. Oxygen, there's 4 of them. They each have 6, so that's 24. And this 3 means we also have 3 more electrons. So 5, 8, and 24 gives us 32 electrons. So that's saying phosphate has 32 valence electrons. Now we have to figure out how many this wants. Phosphorus wants 8. Oxygen, there's 4 of them, and they all want 8. So that's a total of 40 electrons it wants to feel like it has. When I subtract these, I find it has 8 bonding electrons. 2 bonds, 2 electrons in every bond means we have 4 bonds. Pause the video, see if you can draw it now. If you didn't already draw it, that is. Well, phosphorus is the least electronegative one. So we're going to make it all the way around the phosphorus. Oh, we've got all of our bonds, 4 bonds, done. Now it had 32 electrons, so we have to make sure we have 32 on this molecule. 2, 4, 6, 8, 9, 10, 11, 12, 13, 14, that oxygen is good. 15, 16, 17, 18, 19, 20, that one's good. 21, 22, 23, 24, 25, 26, that one's good. 27, 28, 29, 30, 31, 32. We're not done yet though. Remember, this is an ion. Brackets. Boy, that's a terrible straight line. Oh well, that's even worse. Okay, well, provided you can draw better straight lines, they do need brackets with the 3 negative on the outside. The rest of the video is all extra credit practice problems. So at this point, it's up to you whether or not you decide you want to finish the video. If you feel like you got a good handle on this, you're good to go. If you want the extra credit points, let me see them tomorrow. The next video, we're going to talk about exceptions to the octet rule.